Welcome, my beautiful friends, to our second session to Chemistry Practical, Paper 3. This is our practical paper, Paper 2 or Paper 3, and we are continuing with our Part 2 of our facilitation. And the session is led by Nyirimbibi Isaac, and that's a telephone number or WhatsApp number which you can always use to reach out to inquire on a few things and also for other educational resources that you may be in need of. So in this second session, we shall be continuing from where we stopped from in the first session. So for those who have not watched the first session yet, please go back to the channel and check for the Chemistry Practical Facilitation Session 1. Let's continue from where we stopped from. Yesterday, we looked at the accessible areas, and we said that we have chemical reaction rates, thermochemistry, we have reactivity series, we have solubility of salts, we have soap detergents and hard water, we have stoichiometry, formulae, and mole concept. And under mole concept is where we find the acid-base reactions or even the titrations. So in the previous session, that is session 1, we were able to cover all these, the thermochemistry. We covered the thermochemistry, and I left an assignment of last year's paper, that is 2024, which was talking about the heat of displacement. Hope we have tried it out, and today we shall be beginning with that before we wind up with the remaining topics, the chemical reaction rates, the reactivity series, and then the hard water. So all those questions will be covered in this session. Make sure that you have where to note and also pay much attention so that we can move together. Maybe just a reminder that this practical book is on market for those who have not yet ordered. Let's order in a bulk. Where bulk purchases, we said they will attract some discounts. So you can call on this number or you WhatsApp on that Airtel number, and I will be able to reach you. So let's go directly to where we stopped from, and we said we shall be beginning with thermochemistry, the number for UNEB. Yes, it is here. This number for UNEB, which was set last year, UNEB Chemistry Paper 3, 2024. We are beginning with this, and then thereafter, we shall be looking at other topics, and we complete all the practical items with sample solutions. Let's go through this item. Rashid is a student who intends to make a presentation during a science fair on alternative energy solutions. He wants to use the reaction of iron with copper 2 sulfate solution to generate heat. However, he does not know the maximum amount of heat generated by the reaction. Iron reacts with copper 2 sulfate according to the following equation. Copper 2 sulfate reacts with iron to produce iron sulfate and copper solid. You have been contacted to help Rashid, and you are provided with the following. BA1, which is 30 cubic centimeters of copper 2 sulfate solution, X, which is iron. What are they asking us to do? Task. I believe we have already gone through this scenario in our first session, so we want to look at how to respond. Task: as a learner of chemistry, design an experiment you will use to determine the maximum heat change for the reaction. Okay, designing. We recall in designing the experiment is where we do our planning phase. And planning phase, it consists of a number of things like aim, hypothesis, variables, risks and mitigations, materials, then the procedures. All those are under designing the experiment. Then part B, carry out experiment and record your results. Now look at this. A minimum of 6 readings is required. So here you have to use a minimum of 6 readings. Okay, then analyze the results and inform Rashid accordingly, which means here we do analysis and then we recommend or we make a conclusion according to our results. So let's see what do we do. But number one thing, we need to see what is the problem in the scenario. This is Rashid, who wants to generate heat through the reaction between copper sulfate and iron. What do we notice in this? That this is copper 2 sulfate reacting with iron. We can see that it is called the displacement reaction. Let me use this red. The displacement reaction. This is iron, which is displacing copper from its solution, and we can see that it is now forming iron sulfate, and then copper solid is deposited. So which means it is called the displacement reaction, and we want to calculate the amount of heat which is released during the displacement reaction. And from the task we can always get even the aim. You see they are saying design an experiment you will use to determine the maximum heat change for the reaction. Which reaction? The reaction has been mentioned in the scenario. That's why we need to always refer to the scenario, the task, and then we generate very good responses. I will not take much time. We shall be going through as fast as we can. Let's go through this. The aim. So we're saying that the aim is to determine the maximum heat change. Are you seeing that? For the reaction between, now, so you don't need to leave out this, for the reaction between iron and copper 2 sulfate. Good. I think we can see how that was stated. We have gotten this aim from our task. Then, which reaction? We have gotten this reaction from our scenario. Therefore, we have to make sure that we read the scenario very well, we read the task, and we get these scores. Make sure that you don't lose out any score. Maximize your scores. Hypothesis. When iron reacts with copper 2 sulfate solution, heat is released due to exothermic displacement. So, surely when you give surge, heat is released. That is our prediction, that when iron reacts with copper sulfate, heat is released. There is that knowledge that we have that it will be released due to exothermic displacement reaction. So they're saying that the maximum heat change depends on the amount of iron added until all copper 2 sulfate is reactive. That is my explanation to you. It doesn't mean that now even you're going to start writing all the explanation. It is explanation that I'm giving to you. Let's look at the variables. I believe now we are very good at writing variables. Please, for those who have not yet gone through session 1, first go back, because all of these terms have been explained very well in session 1. So here we are just going ahead to try out examples on each and every subtopic, on each and every accessible area. For those who have not yet subscribed, subscribe. Click on subscription button, and then you click also on notification button. Now the notification button will help you to get the notification, the update for any new video that is uploaded. And don't forget to share. Sharing is a key. I'm sharing something with you. Also, don't forget to share the same with your friend, and you have blessings. Now, what is the independent variable? The mass of iron added. So the mass of iron added is the one which is going to be changing. We say that independent variable is that which we keep on changing, the one that we manipulate. In fact, we always use the word the manipulated variable. So the mass of iron is the one we're going to be changing. When we change the mass of iron, it will be affecting what will be responding is the temperature that you're going to be measuring. The temperature change, and therefore it becomes the dependent variable. Now, when you're carrying out this experiment, we are going to keep the volume and concentration of copper 2 sulfate constant. We are not going to change. What we do for the mass of 1 gram, it should be the same volume and concentration for the mass of 2 grams, the mass of 3 grams. So you are keeping this one constant, and here you get all your 3 marks. You get all your 3 scores. Then after that, we can talk about the apparatus and the materials that we are going to use. We already said that BA1 is the 30 cubic centimeters of copper 2 sulfate. So, and then XC is iron powder, or it can be iron fillings, depending on what they have given you in the exam or what is available to us. Then we have the plastic beaker, we have the measuring cylinder, we have the thermometer, the spatula, the one you're going to use for removing the iron, and then the electronic balance, the one we're going to use to measure stopwatch, glass rod or for steering, and then the filter paper. Now, these are the materials. You don't need to cram them, but when you're carrying out this experiment, what are some of the materials that you can use that will be in need of? What do you have at school? Those are the available materials to carry out the experiment. Because it's not a must to use what I'm using, you can use another other materials, but you get the same. Maybe you could be having polyester cup. Maybe you're having any other cup instead of a beaker. What are you having at school? Use that one, and you make sure whatever you put under the materials up there is what you're putting in here. In the procedures, you need to reflect what you have listed. Otherwise, if you put a beaker up and then here you put maybe a calorimeter, which means this person doesn't know what he or she has used, doesn't know the materials he's using, just using cram work. So not to show that you are cramming, what you do, you make sure that materials you have listed are the ones you're using even the procedures. Now, let's look at what to do. What to do, we are saying that 30 cubic centimeters of copper 2 sulfate solution is measured and poured into a plastic beaker. Is measured. And the initial temperature of solution is recorded. Good. 0.5 grams of iron powder are weighed and added to the solution. So for me here, I have used the powder, which means even up there on the materials, you need to use powder. Don't show two things, which means you need to use the what? Powder. Don't put powder or iron fillings. When you're in the exam, the material they have given you is the one you record. So if you have given you the powder, record the what? Powder. If they have given you the iron fillings, record iron fillings. So you don't need to see powder or this. This is for just my explanation here. Then the stopwatch is immediately started as the solution is stirred gently, monitoring the temperature change. Then the highest temperature reached is recorded and noted. Steps 2 to 4 are repeated with 1 gram, 1.5 grams, 2.0 grams, 2.3 grams. But you recall keeping this volume of copper 2 sulfate constant, which means we can even say steps 1 to 4 because we are repeating even step 1 but keeping this volume what? Constant. So the volume we have used for 30 on 5 grams should remain 30 on 1 gram, should remain 30 for 2 grams, for 30 on 3 grams. So it will be constant. And you can see this is the first experiment. This will be the second, the third, fourth, fifth, sixth. And you recall they told us to do at least 6. So which means we are safe. We are safe and we are good to go. Good. and you get all your scores. Don't mind about how many scores you get, so long as you write a good, you write what you're supposed to write. Then risks and mitigations, these ones I no longer waste much time on them, because you're the one who knows what material, which apparatus are you using, what are some of the risks that may occur. Is this one, that the reaction may get very hot. If you know that may go to be very hot, then use small quantities. You can use the small quantities. Then, since we don't have polystyrene in camp, for us to have used the what? We have used the plastic what? Plastic beaker. So those are things that I just want to help us know. And I was saying that contact with copper 2 sulfate can be toxic. So what should you do? You need to wear gloves and avoid skin contact. Are you seeing that? Then there could be spillage of chemicals. So what do we do? Work on a tray and clean spills immediately. Are you seeing that? Then there's inhalation of iron powder. What do we do? Handle carefully in a well-ventilated area. We don't need you to write to draw a table. Now you find some learners starting to draw tables, writing very many points. You may have only 2 points. A one risk which is mitigated very well. Or you can have 2 risks which have been mitigated very well. So what we want is to see that a learner can identify some of the risks and also is able to mitigate, is able to identify the solution to those risks. Results. Now, this is the sample table. When you're at school carrying out this experiment, you can get different results. But this is the sample table that we are having. This table, you can see it is having, okay, this is good. It is having mass of the iron. You can see we have 1, 2, 3, 4, 5, 6. They asked us to do at least 6 intervals. I believe those are 6. Then initial temperature, we code initial temperature, of course, according to the procedures. And then we code the final temperature. And then you can be able to get the temperature change. So we got temperature change for the first, temperature change for second, temperature change for the third, temperature change for the fourth, temperature change for the fifth, temperature change for the sixth. Of course, even these ones, you're measuring them. So we're able to give you some scores. And when you have that, there's one thing I want to remind us. When you're drawing table of results, don't forget to show mass of iron in what? It is in grams. Some learners normally forget that, and they forget to include the units. If you don't put units, I'll give you a 0. Make sure you take note of that, because now you say mass of iron, you just put 0.5. What are they? Are they kilograms? Are they atomic mass units? What are they? So put the units. Initial temperature in degrees Celsius. Good. Final temperature in degrees Celsius. Temperature change in degrees Celsius. So that is our table of results. Are you seeing how things become nice? Now, the analysis, we can have a graph. My graph has been generated using Excel. I believe we can use our Excel to do this. But a learner in a paper, you're not going to use Excel. Me, I have used what? Excel. But I believe this Excel of mine, it can show the trend. You can see when it was 3 grams, I'm just looking up here. Maybe let me just bring a table a little bit. Let's see. Okay, there. When it was 3 grams are here. The temperature change is 12. I think very good. When it was 2.5, the temperature change was 12.1, somewhere there, like that. So you can see my graph is clear. Though for you need to use your graph paper. You need to use your graph paper. And I believe right now, you know what you need to show on the graph. You can see my graph is having all the things. Number 1, it has a title. Your graph should have a title. you should label the axes. Let someone know that on the vertical, because we said vertical is where we have the dependent variable, while down here on the horizontal is where we have the independent variable. The independent variable of ours was mass of iron. The dependent variable was temperature. So the dependent variable goes on the vertical, independent variable on the horizontal axis. I believe that is clear. So from there, we can talk something small, and we say, I'm just going to read through, that the reaction between iron and copper 2 sulfate is exothermic. Isn't it true? It has released some heat, as indicated by temperature rise. Okay. The maximum temperature change, 12.0, was achieved with 2 grams of iron. Further addition did not increase temperature significantly, indicating all copper 2 sulfate was reacted. Are you seeing that? At that point, which means 2 grams of iron are the ones which were needed to react all the copper 2 sulfate, which was present in 30 cubic centimeters. Actually, it is here that therefore 2 grams of iron is the optimum amount for maximum heat generation with 30 cubic centimeters. That is good. That was a very good analysis using our graph, and we are able to see my graph. This point is very well written. This point is very good. This one good. This point good. This point good. This point here good. Of course, I gave access. Don't think that the ticks I'm putting are equivalent to the scores you're going to get. They have the maximum. But what I don't mind about how many scores are there, mind about writing correct things. I think that is all I can talk about that. Then what conclusion can we give to Rashid? Then we are just saying that this is the conclusion. We can say that to generate the maximum heat during the demonstration, use 2.0 grams of iron with 30 cubic centimeters of copper 2 sulfate. Are you seeing that? Adding more iron will not increase the heat generated. In simple terms, if you have 30 cubic centimeters of copper 2 sulfate of this concentration, are you there? And you add more than these grams, you're just wasting resources, because only 2 grams are enough to produce the maximum heat required. I think how doing this experiment was very important to help Rashid. So surely I believe you have been able to get something about this experiment. And one thing I want to encourage us is to keep on looking for more scenarios. Look for more scenarios, try them out. If you get issues, come back to the video and watch. Those who are requesting for PDFs, you can inbox on my numbers, and then we discuss on how you can get those PDFs. Otherwise, just keep on pausing, and then you'll be able to move on forward. Yeah, now we go to the essence of this session. The essence of this session is to look at other topics that were not tackled in session 1. Don't forget the one we have just finished for UNEB was for thermochemistry, which we did in our session number 1. But in session number 1, we didn't look at hard water. Now, today I'm not going to teach notes about hard water, but one thing I know that is that we know what hard water is. And if you don't know, I just request you to go back to the notes and read about hard water. Maybe a simple clue about hard water before we begin. One thing we know about hard water is that when we are looking at hard water, we can't look at hard water without talking about soap. Because on hard water, we are seeing that the ions which cause water hardness are the calcium ions and the magnesium ions. And we know that when we are doing our laundry work and we are washing with hard water, the soap, or the bar soap, when you use it in hard water, it will react and it form what we call scum. Now, when scum is formed, it prevents the production of, like that time, more soap is used in formation of the other one, scum, and it prevents the formation of lather easily, which means waste, which can bring about wastage of our resources, the money which have bought the soap. So in this area of water hardness or hard water, we are looking at how can you know that this water is hard. Okay, you have two water samples, maybe A, B, C, and maybe these people are having issues of water hardness, and maybe they are washing clothes and they are leaving there some spots, and they have asked you to help these people know which kind of water source can they use. So which means if you want to test for water hardness, what do you do? We are going to see that. But also there's when the village has water which is hard, and then of course there's nothing to do other than living with what is there. But how can you live with what is there when it is wasting your resources? Then we see how do we remove the water hardness. So in this we are going to look at two items. One looking at how to identify hard water. Another one will be looking at how to remove water hardness. Let me hope you're going to keep on pausing and you note down. The question is there with the task. You can note it down, try it out first before you look at my responses, so that at the end of it all, you can be able to respond to score yourself. Let's do this faster. I'm going to read. Juma is a resident of Kabaya village in western Uganda, Kisoro district. He washes clothes in the nearby trading center for money. Due to water shortages in his, not her, in his area, please you'll change that, in his area during dry season, he treks for long distances looking for clean water so as to satisfy his customers. There are 3 water sources available in the trading center where most of his customers live. Okay, he wants to understand which of the 3 water sources would be better to use when washing clothes for maximum profit. You are provided with a sample of each of water sources labeled solutions A, B, and C, and a soap solution labeled FA1. Now, are you seeing this? Now, in this scenario, we can see that Juma has been provided with 3 water sources. Water from 3 sources. Are we there? Now, one is labeled A, B, C, and now he wants to find out which one is the best. Which one can he use for washing his clothes and maximize the profit? Okay, which means we need to look for the one which is soft compared to others. Task. Plan and carry out an investigation to find out which of the 3 water samples easily forms lather with soap, and use your results to recommend the appropriate water Juma should use to avoid wasting soap. Now, in this item, we have not separated the parts, part A, part B, part C. But I believe after going through this, because already in the session number 1, we were able to talk about what we need to talk about. The aim, the preliminary work, the planning phase, then the data and analysis, and then the conclusion and the recommendation. So I believe we can do that because this question was, the task was general talking about everything. Carry out investigation, then use the results, which means you need to get results, and recommend. You need to recommend after analyzing. Are you seeing that? So can we go direct to the response? What is our aim? It is there. The aim is to determine which of the 3 water samples. Now, I've seen some of the learners saying which of the 3 water samples easily forms lather. You're not telling us the water samples. You need to tell us which of the water samples A, B, and C easily forms the lather with soap, and you get your nice score. So my emphasis is on this, that we need to also talk about these samples. The first sample is from A, another sample is B, another sample is C. And what are we finding out? Which one forms lather easily with soap? Number 2, we look at the variables. Now, the variables, the independent variable, what are we keeping on changing is the water from the different source. Are you seeing that? There was water sample A. When you put it there, it will behave differently. When you use the round for B, it will behave differently. So what will be changing? It will be the dependent variable, the responding. And now we are saying that hardness of water samples A, B, and C, or the concentration of ions responsible for hardness in water samples. So we can use any of the 2. It doesn't mean now you start writing that 2. Choose one. The hardness of water samples or concentration of the ions responsible for hardness in water sample A, B, and C. Then the dependent variable, what are we going to be measuring is the volume of soap solution used. Are we there? The volume of soap solution. Sorry for that. The volume of soap solution used, because you recall that we have soap solution and we have these water samples. So which means we shall be testing which one forms lather easily. So the one which takes little volume of soap solution is the one which is better compared to the one which will take very much or too much volume for soap. Controlled is water volume of water sample. I believe that is it. If you're testing using 20 cubic centimeters of sample A, let it be the same for B, be the same for C, and then you determine the volume of soap used. I think that to form persistence lather. I think that is clear. So there you get your scores on the variables. So the one who was talking about the issue is on water hardness on the soap. I believe you have been catered for in this tutorial, in this facilitation. Then we have hypothesis. Hypothesis, what do we predict? So I think that soap reacts with hard water, forming an insoluble substance. With hard water, that is number 1. But now you recall, you don't know which one is between A, B, C. So the one which is hard, it will form an insoluble substance. Then in absence of ions responsible for hardness, in simple terms, in soft water, it reacts with water to form lather easily. I think that is very clear. So that is our prediction. Our prediction is that when soap reacts with hard water, it will form scum. Scum, the insoluble substance we are talking about. But in absence of the ions responsible for water hardness, then it will form lather easily. Procedures. Now, look at this. We're having 20 or 25. Do you need to put 20 or 25? The day you put 20 or 25, it means you don't know what you're doing. And if I'm the one marking you, I'll first give you a 0 there. Okay. I'll give a 0 on that part here. Because there's no how you can use 20 or 25. Instead, you'll use either 20. When you're pipetting, you use a pipette for 20 cubic centimeters, or you use the one for 25 cubic centimeters. So what does it tell us? That when you're carrying out this experiment, make sure you read the units on your pipette. Are the units on your pipette the 20 cubic centimeters, or they are 25 cubic centimeters? So the one you are using, use that, and you record only that you're using. So 25 cubic centimeters of water sample A is pipetted into a clean conical flask. Then the burette is filled with solution FA1 to 0 mark as initial burette reading. The water is titrated with a soap solution from burette while shaking the conical flask to mix until permanent lather is formed. The final burette volume for soap solution used to form permanent lather is noted and recorded. Okay. The resultant mixture is powered and conical flask washed thoroughly. Good. The procedures A to E are repeated for each of the water sample B and C. I like that. The volume of soap solution added in cubic centimeter is recorded. I think these procedures are very well written in very good tense. So make sure that you also do the same. Risks and mitigation: pouring soap solution on clothes or paper and wetting the tables. That is a danger. It can be mitigated by use of funnel when pouring soap solution into the burette. That is it. But also you can have another risk: breakage, not blockage, breakage of conical flask. How can we mitigate that? By handling a conical flask carefully. Okay, we go to presentation of data. Now, on presentation of data, we are saying that the results are recorded in the table below for the water samples ABC. Volume of pipette used. Now here, I have written it even here. So we are saying that here we don't put the 2. We put the one we have used in the experiment. So when you have used 25 here, if it is 25, even here we record 25. We don't put the 2. I think that is clear. Then we come on the table of results. So on the table of results, we have the type of water, ABC. Then we have the final burette reading in cubic centimeters, initial burette reading in cubic centimeters, volume of soap solution used in cubic centimeters. And then you can, the initial and final. So that is the volume of this used, volume of that used, and volume of C used. So you're able to get all your scores. I normally give a score on units because someone knows how to put units and another score outside the box, showing that this learner knows how to design the box very, very well. Okay, now let's look at data analysis and interpretation, and then conclusion and recommendation. So data analysis and interpretation, we already have our table, so we can now come and say the volume of soap required to form lather with water sample A is this. Good. The volume of soap required to form lather with water sample B is 23 cubic centimeters. Volume of soap required to form lather with water sample C is 15 cubic centimeters. Then conclusion. The water sample C requires the least amount of soap to form lather. Therefore, it is the best water sample to use. I think that you can make conclusion from there. Now, recommendation. Based on the above results of the experiment, I therefore recommend Juma to use water sample C, yes, for washing because it easily forms lather. And you get all your scores. I think how you get all your scores in just a few minutes. So please, just what you need to do is to read very well the scenario, and then you'll be able to respond very well. Let's look at our second item, still under water, hard water. What is the difference between this item and the previous one? Read through and find out the difference. Let's read through together. Apio is a resident of Nagongela Tororo district. She washes clothes for people as her main income earning job. Her customers have often complained of white spots that remain in their clothes after washing, and she's most likely to lose most of her customers. Her friend Opendi informed her that she can buy washing soda and always add to water before washing. However, she does not know the quantity of washing soda to be added. Apio uses 5 jerry cans of each 20 liter of water every day. You have been provided with BA1, which is washing soda, that is sodium carbonate solution. Mineral in water sample reacts with washing soda according to the equation. The mineral in water sample is here, the magnesium sulfate. So the mineral in water sample, which means this is water reacting with sodium carbonate to form magnesium water. Now water is having the magnesium sulfate ion, the magnesium ions. We say that the ions responsible for water hardness is calcium ions and magnesium ions. And I think that a friend has said you can add washing soda. Washing soda, which is sodium carbonate, and it is here. And they're giving us an equation which shows the reaction between magnesium sulfate present in hard water and sodium carbonate to form magnesium carbonate and sodium sulfate. Okay, sorry for that. Let's look at the task. Plan and design a scientific investigation to guide Apio on required amount of washing soda. So when we are designing, we do the planning. The planning, you recall here we are looking at how to determine the amount of sodium carbonate required. So here, what have they given us? They have given us the washing soda, BA1, and they have given us the water sample. And which means one thing we want to know is how much sodium carbonate is needed to remove the water hardness, the ions present which are responsible for causing water hardness. So our aim is an experiment to investigate the quantity of sodium carbonate required to soften 5 jerry cans of hard water, each at 20 liters. And you get your scores. Then, hypothesis. Increasing the amount of washing soda added to water will reduce on formation of white spots compared with washing without it. So in this hypothesis, we expect, because we know that washing soda is one of the chemicals that we can use to remove water hardness. So in using our knowledge, we recall it is testable statement, a statement that we can test and find out whether it is true or not. So from that knowledge that we know that this washing soda can be added to remove, so I think that if it is added, then the spots will reduce compared to when we wash without using it. Okay, what are the variables now? The variables. So the variables, we have 3 variables: the dependent, independent, and controlled. So independent variable is volume of hard water measured. Good. The independent variable is volume of sodium carbonate solution added, because depending the amount of hard water measured, it will also help us to know the amount of sodium carbonate needed to remove the hardness, the ions present in the water that cause the water hardness. What are you keeping constant? The water hardness or the concentration. The concentration is going to be left. The concentration of ions in hard water is going to be left constant. What are going to be changing? The volumes. Like the concentration is the same. You have like 20 liters with the same concentration. Are you seeing that? Then what you will do on the same jerrycan of 20 liter, test using maybe 1 liter, test using 2 liters, and then you see how much sodium carbonate is needed in 1 liter, how much sodium carbonate is needed in the other one. So the volume of sodium carbonate needed will be changing depending on the volume of hardness water, of hard water measured. So there you get all your scores. Then requirements: we need measuring cylinder, we need conical flask, we need the bullet, retort stand, we need sodium carbonate, and we need hard water. We need the hard water. So after that, there's part B that's saying conduct the investigation on the water sample provided. So we need to look at the procedures. They're saying that 20 cubic centimeters of hard water is measured using 100 cubic centimeters of measuring cylinder and transferred into a conical flask. Are we seeing that? Then solution BA1 sodium carbonate is filled into a bullet and adjusted to 0. Is filled into a bullet and adjusted to 0. And then BA1 is then run into hard water in conical flask and was shaken until a white precipitate was formed. So when you react sodium carbonate with the ions present in the water, which we are calling the magnesium ions, and we are calling it magnesium sulfate, they form a white precipitate. So we are going to titrate using that. The hard water which is in the conical flask, we titrate it with what? We run the sodium carbonate which is put in the bullet. Now the bullet reading is noted and recorded. So when it changes to white precipitate, you recall we have first used 20 cubic centimeters of hard water. You're just having your hard water in one, maybe in a big beaker. So you keep on removing some. For the first time 20, for the second time 30, for the fourth time 40, 50th time 50, like that. So that you can get a number of readings, experiments looking at how much sodium carbonate is needed for each. So the procedure A to C was repeated for 30, 40, 50, 60 respectively. Then what are the risks and mitigations? Acid powering on the skin or question paper. You need to put on gloves and closed shoes. I believe now no one should get a 0 on risks and mitigation. Put all of them, the ones you think can happen during your experiment. Now, treatment of results obtained in B. So that is our question part C. So we draw our table. And so volume of hard water, you recall we have been looking at it, 10 cubic centimeter, 20, 30, 40, 50, 60. Those are 6 intervals that we have done. So when that was 10, the volume of BA1, which is sodium carbonate used, was 1 cubic centimeter. For 20, 2. For 30, 3. For 40, 4. For 50, 5. For 60, 6. So that is the table of results showing the amount of sodium carbonate needed. Now, how do we analyze our results? So I'm saying that a graph can be plotted. So here is our graph, and the title is a key. We are saying that a graph of volume of hard water against volume of BA1 solution. We have all this in our table. Volume of hard water and volume of BA1 used. So what happens? We draw very well and we label our axes, volume of hard water, volume of BA1, and then we can join our lines. I'm not going to go through that because we said at 10 it was 1, at 20 it was 2, at 30 it was 3, at 40 it was 4. Very clear. I believe the graph is very clear. Make sure that you do the same. What conclusion can we say? But are you saying that there is some consistency? When it is 10, you have used 1 cubic centimeter of sodium carbonate. When it is 20, 2. Are you saying that there is something which is uniform? Okay. Now, what do we do? What conclusion can we make? What can we analyze from that graph? So I say that from the graph and the table of results of the experiment, the volume of BA1 added to soften hard water is directly proportional to the volume of hard water softened. I think that is clear. Is directly proportional. If you are using 10, you need 1. For 20, you need 2. For 30, you need 3. I believe you can know. For 50, you need 5. For 60, you need 6. For 70, you need 7. So, after looking at the first 3, you can get to know what will happen for the remaining ones. But you call for last, we are looking at how many liters, because there are 5 jerrycans, each jerrycan carrying 20 liters. Now, from our table, each 10 cubic centimeter of hard water required 1 cubic centimeter. So that's what we are looking at. The research showed that 10 cubic centimeter of hard water required 1 cubic centimeter of sodium carbonate, which means it is a ratio of 10 to 1. Now, it means that 5 jerrycans, which is 5 times, because each jerrycan has 20 liters, each liter has 1,000 cubic centimeters. So we can convert 5 jerrycans into what? Cubic centimeters. So which means it will be 5 times 20 times 1,000 to get the volume of water used. The volume of water used by this girl. Now, after getting the volume of water used, the hard water, you recall that it is a ratio of 10 to 1. Every 10 cubic centimeter of hard water needs only 1 cubic centimeter of sodium carbonate. What about this volume? Which means we divide it by 10. That's why you're having this value divided by 10, and then you're able to get the volume of sodium carbonate needed by this girl to wash using the 5 liters. This 10 is just over here. It is over down here. Computer. But you extend this 10 here. It is 10. It's supposed to be down here. So make sure that you put it there, so that when you have 100,000 divided by 10, then you're able to get 10,000 cubic centimeters of sodium carbonate solution. I think that is very clear. And now they want us to convert it to liters, that if 1 liter is equal to 1,000 cubic centimeters, what about the 10,000 cubic centimeters? It will equal to 10 liters, which means every 5 jerrycans of water, she needs only 10 liters of sodium carbonate. I think here we can see the recommendation that basing on the above results, I therefore recommend it's not Atimago, it is Appeal. I therefore recommend Appeal, so we can put the right name. We recommend Appeal. I recommend Appeal. Let's put Appeal. Good. So basing on the above results, I therefore recommend Appeal to add 10 liters of solution BA1 to the 5 jerry can, 20 liter each, to add water she uses, and this will save her from wasting soap. Soap and avoid chalk marks on those clothes of her customers. I believe that was very, very clear. So in this session, and especially on hard water, we have seen two things: identifying which one the hard water, hardness in water. Then another experiment, this one we have seen how to remove hard water. We can remove hard water by adding washing soda, which is sodium carbonate. And we have seen that when sodium carbonate reacts with the magnesium sulfate, it forms a white precipitate. Okay, now let's go to our next chapter, which is reactivity series. Now, when a question comes in reactivity series, what comes in your mind? In reactivity series, we are looking at, actually, what is reactivity series? Is a list of elements of metals, which is showing the order of increasing, which are arranged in their increasing order of reactivity. It can be in the increasing order of reactivity or in the decreasing order of reactivity, but most especially we normally consider that from the decreasing order, from the first we are more reactive to the least reactive. Now there's one thing we know, that these reactivity series are also referred to displacement reactions. What do we mean? In displacement reactions, the one which is more reactive displaces the one which is least reactive. We saw this in thermochemistry, but now in thermochemistry it was talking about heat of displacement reaction. There we are specifically calculating amount of heat that is being released. Then here we are looking at, we can use this experiment to determine which one is more effective than the other. Which one, because the one which displaces the other then becomes the better alternative. So let's read this item, and then we say, if a question comes under reactivity series, how can we approach that question? I want us to read it faster so that we can see how to wind up with this. So we're saying, Mukwano Group of companies in Uganda are the leading manufacturers of cooking oils using locally available agricultural produce such as simsim, groundnuts, and sunflower seeds. The company started adding value to oil by turning it into margarines and Blue Band. The process is done by adding hydrogen gas to liquid oil in order to harden it, a process called hardening of oils. Hydrogen is obtained by reacting metals with an acid. Due to high demand for Blue Band and margarine from the customers, the company has decided to purchase metals for the production of hydrogen gas instead of importing it. 3 metals L, N, and M were purchased, but the workers want to know the metal that can produce the hydrogen gas faster per day. The acid reacts with metal as below. Metal reacts with an acid to form metal chloride and hydrogen gas. You are provided with Fa1, which is hydrochloric acid solution, and metals L, N, and M. Task: As a chemistry student who has studied reactivity of metals, plan and carry out a scientific investigation on metals L, N, and M using Fa1, which is a solution of hydrochloric acid. Write a report and include your recommendations on which metal the company can use. I think this question was very clear to us, and from this task you can be able to generate the aim of the experiment. And then you can also get to know the variables, and also we shall be able to get down variables, hypothesis, and all the preliminary work or the planning phase. Let's start with that. Number one, we need the aim of the experiment. So I'm saying that the aim of the experiment is an experiment to investigate which metal can be used to produce hydrogen gas faster in a short time when hydrochloric acid reacts with metals L, M, and N. I'll add you a mark. I think that so you don't need to end without mentioning which metals I'm going to use. So that's why it was very important for us to include that and we get all the scores. Number two is hypothesis. So I'm saying that the metal L reacts with hydrochloric acid faster than metal N and M. Now the question is, why have you considered L? You call hypothesis, we said it is a testable statement. Now, it is based on knowledge. So which means a learner is given these metals L, M, and N, because this is a question many people are asking. How do you know that this one is the best? You can know by looking at them. Maybe sometimes you can have the one which is in powder form, the one which is in solid form, and then in crystalline form, and maybe the difference is the texture, the surface area, and then you can use the knowledge, that's the surface area, how it affects on the rate of reaction. So depending, we can use our knowledge to make a testable statement. So this is a testable statement which was used, and you can see it is a very good one. So when they give you these elements L, N, and M, you can be able to know which one by looking at those metals. Variables, we have dependent variable, and we're saying that dependent variable is the time taken for gas bubbles to stop. Then independent variable, metals L, N, and M. Then the controlled is the volume of hydrochloric acid. So what are we going to be doing? We have three metals. So what we are going to be doing is measuring volume of hydrochloric acid, which is the same, we keep it very constant. So if you're using 50 cubic centimeters, then you add the metal N. Of course, the metal, even the mass of these metals that you're going to use should be kept constant. But now we are talking about what is independent, metal L, N, and M reactivity. But their masses also has to be constant. I think we need to add the mass. We can add the what? The mass. Not going to write that, but you can write it down. So the volume of hydrochloric acid and the mass of these ones are going to be constant. Then what we are going to be changing are the metals themselves. And you know that each metal reacts differently with the acid. So depending on the reactivity, it will also help us to determine or to measure the time taken for the gas bubbles to stop. So which means the one which takes less time for bubbles to stop, which means is more reactive. It reacts faster and stops. Then procedures, we are saying that 0.5 grams of metal L were weighed on a beam balance and transferred into 250 cubic centimeters clean conical flask. Then measured 50 cubic centimeters of, or we can say 50 cubic centimeters of solution Fa1 were measured using 100 cubic centimeter or 50 cubic centimeter. I believe we know very well that now this, for you when you're giving yours, you don't need to keep on using O. Here we put O so that those people who are having 50 cubic centimeter measuring cylinders, or those who are having 100, they can use any of those. So you just use only one kind of volume, the one you're using actually in your experiment. So, and transferred into 250 cubic centimeter clean conical flask containing 0.5 grams of metal L. Stirred for 20 seconds and immediately started a stop clock. The time taken for the gas bubbles to stop was observed and recorded in the table of results. Now, it is stirred for around 20 seconds and we leave it for, we start a stop clock and we wait until when the gas bubbles stop. Why are we stirring a few seconds? So that they can mix very well. The metal and the acid can mix very well. So what you do for metal L should be the same thing you do for metal N, the same thing you do for metal M. But now with time taken for these ones to be, the bubbles to stop, is also recorded and noted down in the table of results. So the content in the conical flask is then powered away and the conical flask is washed. Then the procedures A to C are repeated for metals N and M respectively. What are the requirements needed? Now here you don't need to put all of these two things. Choose one, the one you're using. So you have measuring cylinder, 250 cubic centimeter of conical flask, a beaker. Now don't put a cup or a beaker. Put a beaker if it is the one you have. Then metal L, N and M. We have bin, balance and solution Fa1. So those are the requirements. What are some of the risks? There is spilling solution Fa1, which is the acid on the table, or pouring on the skin or question paper. How do we mitigate that? Put on lab coat, we can put on gloves and the closed shoes. So those are the risks and mitigation. Then presentation of data and recording of data. I want us to go through this faster. So I'm saying that the results are recorded. The results are recorded. We can use a good recorded in the table. And then we're saying that the graph of volume of Fa1 against time taken for the reaction to stop is plotted. Then the mass values are recorded to 1 decimal place. So we can just get to tell us which decimal place you have used. So it is also recorded. So that is our table of results, showing the metal, showing the mass, this is the mass of metal weight, then volume of Fa1 added, time taken for the bubbles to stop. So you get all your scores. Then we can have even the graph for analysis, a graph for volume of the volume of Fa1. Now volume of Fa1, this one should go off, of Fa1 against time. So Fa1 is HCl in cubic centimeters against time. Please make sure that you edit on that such that you don't have a long thing. That's why I said let us always make sure that we don't just copy and paste. Instead, we always look through. If there's any error made somewhere, let me know in the comment section and then we can be able to rectify it if I have not seen that kind of error. So here we have the metal L, we have the metal N, and we have the metal M and the metal N. So we can see that we can have a graph and we can see which one is taking less time. Metal L has taken 10 minutes. So since it is taking 10 minutes alone, which means it is the best compared to N that takes 40 minutes for a complete reaction. Then that analysis, we can say that the graph of volume of hydrochloric acid against time for the bubbles of hydrogen gas to stop from each metal to complete a reaction shows that metal L reacts rapidly, metal M reacts moderately, and metal N reacts very slowly and takes a longer time for bubbles to stop. Then this implies that metal L is more reactive than metal M and N respectively. Okay, good. Now, conclusion. Basing on the above results, I therefore recommend that metal L be used for production of hydrogen gas, since it reacts with hydrochloric acid faster than metals N and M. I believe that was a very good analysis on how we can discuss questions which are related with reactivity series. Let's look at our chapter 4. Now, these other topics that we are not going to talk about, like acid-based reactions, titrations, and more concept. In our upcoming sessions, we shall be going through like one of them, two of them, so that you can still get a clue on how such questions are set, but also a clue on how such questions can be responded to. So please make sure that you keep on checking on the channel, so that whenever it is out, you're able to get it as the first person. Chemical reactions. Let's read through faster. So it is saying, the military barracks urgently needs more supply of sulfur for the manufacture of gunpowder at the military gun factory. You are provided with the following chemical solutions used for the production of sulfur. Ba1, sodium thiosulfate, Ba2, dilute hydrochloric acid. Then sodium thiosulfate reacts with hydrochloric acid to form sulfur, which makes the solution yellow according to the equation. Task. You are required to investigate how the rate of reaction varies with temperature during the production of sulfur and make your recommendation based on your experiment. Now, in chemical reactions, we are looking at factors that affect the rate of reaction. Actually, that's all that it is about. And we have different factors like temperature, we have concentration, we have catalyst, we have surface area. Now, all those in those different areas, we can have a question come from anywhere from those areas. So what do we do when a question comes? So let's look at the response. We have already read the task that you are required to investigate. You can say, surely, they are giving us even some clue on how we can respond. To investigate how the rate of reaction varies with temperature during the production of sulfur, and make your recommendation recommendations based on your experiment. We're going to go through them faster, and then we see how best we can wind up. So I say that aim is an experiment to investigate. We are looking at investigating the effect of increasing temperature on the rate of production of sulfur. I think that on the rate of production of sulfur. Then hypothesis: from the theory, we know that if you increase the temperature, even the rate of reaction also increases. So that's why you have that increase in temperature of reaction increases the rate of production of sulfur. That is very clear. So what is the independent variable? Independent is what we keep on manipulating, what we keep on changing, and in this case you can see we are changing the temperature, because we're looking at the effect of temperature on the rate of reaction. Then the dependent, when you change temperature, then even the time taken for the cross to disappear will change. Then controlled variable, it is a volume of BA1 and volume of BA2, which are kept constant. What are we changing? It is only the temperatures. Requirements: we have measuring cylinder of 100 cubic centimeters, the one for 50 cubic centimeters, 250 cubic centimeters of conical flask, stopwatch or clock. Now even this one is not allowed, but I put them there so that you use any that you have in your school. Then you have heat source, pen, paper. Now we may note, okay, pen, paper, thermometer, and then solution BA1 and solution BA2. Then we have risks and mitigations. Risks and mitigations, I believe now we can do a lot with risks and mitigations. Identify, here you're using a thermometer, you're using a conical flask, and all these can easily break. So handling them with care is paramount, it is crucial, and therefore we have to make sure that we identify the risks, we identify the mitigation. Then procedures. Let's look at the procedures very fast, and then we see how best we can deal with other items. So the procedure says a cross X was made with a pen on the white paper and pressed on the table. Then a 250 cubic centimeter conical flask was pressed onto the cross. Using a measuring cylinder, 50 cubic centimeters of BA1 was transferred into the flask, which is over the cross. Using another measuring cylinder, 5 cubic centimeters of BA1 was measured and added onto BA1 in the conical flask, and immediately started the stop clock. The mixture was shaken and conical flask pressed back over the cross. Then the temperature of the maximum of the mixture was noted and recorded. The cross was viewed from the above through the mixture, and the time taken for the yellow coloration to just make the cross invisible was noted and recorded. Then a fresh 50 cubic centimeters of BA1 was transferred into a clean conical flask and solution heated at 30 degrees Celsius. So we are looking at now the temperature. Okay, after raising the temperature, 5 cubic centimeters of BA2 was added to the hot solution of the same at the same time started the stop clock. The mixer was shaken to mix and the flask pressed back over the cross. Looked at the cross from above through the mixture. What did you see? Noted and recorded the time taken for the yellow coloration to just make the cross invisible. And they are saying that the time in seconds for the reaction to occur at 50 degrees Celsius. Then we have procedure F to I is repeated for temperatures 40, 50, and 60 respectively. These results are recorded. These results are recorded in the table below. So this is a table that we can have for search. We have, what are we changing? We are changing the temperature. And when you change the temperature, time taken for the yellow solution to form, it is the one that we are recording as the dependent variable. So here we have the three laws: the one for temperature, the one for time, and then the one for the reciprocal. Then part G, we are saying that calculate the reciprocal of time, 1/t for each temperature, and record in the table above, which is already done. Then plot a graph of A/t against temperature. Now when you talk about this, you have to get a line of best fit and becomes very straight. So when we call out this experiment and you're drawing a graph, make sure your graph has the things we have been talking about. The title, the x-axis is labeled, the y-axis is labeled, the scale is mentioned here, the scale is mentioned such that whoever is marking or scoring will not have anywhere to say, maybe this learner did this, maybe I didn't see this. Make sure that everything is recorded. Okay, conclusion and recommendation. So I'm saying that state how the rate of reaction varies with temperature. So basing on the above results, the rate of reaction is directly proportional to the temperature, or the rate of reaction increases with increase in temperature, which is an agreement with the hypothesis stated above. Are you seeing that? So I believe that was a good one, because it is in our conclusion we have made a prediction, but we have been able to prove our prediction that it was actually correct. Recommendation: basing on the above hypothesis, I therefore recommend that the military factory should increase the temperature of reaction of mixture of thiosulfate and acid in order to increase faster production of sulfur. So I believe whenever we are making conclusions and recommendation, I've seen many learners, they write too much word, they write a lot, but they forget that in chemistry we are marking key points. What are the key points, key ones that you have used? So I want to inform you that we have come to the end of our facilitation of chemistry paper 3. Any other arrangement will be arranged, but for our facilitation for paper 3 is done. Please make sure that you share with your friends. Share with your friends. You like the video, you comment, and subscribe. Please subscribe and you click on the notification button. But most of all, don't forget to share with friends, such that your friends can also keep on sharing on the same work that we are discussing. Otherwise, for those who have been with us right away from session 1 and now we have come to session 2, just know that time you have invested is not in vain. And as I said in my quote, that you are always what you think about. If you know that you can do it, then the success is waiting for you. Otherwise, I want to wish you the best in your assessments. Jah bless.